Good afternoon, everyone. Welcome to another episode of QuEra's World Tour. Today, we are focusing on India and the quantum activities happening in India. My name is Anshuman Singh. I'm a senior photonics engineer at QuEra Computing, and I'm happy to introduce our guest for today's webinar. So, we have Dr. Satyam Priyadarshi. He's CEO of Reignite Future and senior advisor at Global Quantum Intelligence. We have Mr. Amit Saxena for Center of Development of Advanced Computing. His scientist is there. We're also joined by Mr. Shridhar Sivi from Tata Consultancy Services. He's Head of Alliances, Incubation, Research, and Innovation at TCS. I'm also joined by my colleague Tommaso Macri, who is Executive Account Manager at QuEra. So the agenda for today's webinar is as following. So first, I will present some general concept of neutral atom quantum computing from the perspective of QuEra. Then the word will pass to our guest. First, it will be Dr. Satyam, then Mr. Amit from CDAC, and then the Mr. Shridhar from the TCS. At the end, I'll pass the torch to Tommaso to speak about the opportunities and collaboration and making some concluding remarks. First, few words about QuEra. So we are a quantum computing company based in Boston. We have 70 plus employees, and being in Boston, we enjoy very close collaboration with the universities such as Harvard and MIT. Recently, we have opened our offices in UK and Japan as well. Uh, we have a very clear goal in mind to build and commercialize the quantum computing based on neutral atoms, which are scalable. That means large scale of qubits and sufficiently resistant to the noise. Dozens of organizations and hundreds of users already using our quantum computer. The one you see in the right, shown in the Times Square during one of the announcements we made last year in December. If you are listening and interested working with us, I'll encourage you to look at our career page at QuEra.com. So let me walk you through some of the technological challenges of quantum computing with neutral atoms. So neutral atom, first of all, is very promising approach. All the atoms are identical, unlike the artificial qubits, such as in platform is superconducting. And when these atoms are exposed to external electromagnetic field, they all behave in the same way. That means you don't need any individual characterization. They're easier to scale. Today we have machine with hundreds of qubits, and our partner labs have shown thousands of qubits already. And this can be scalable to more than 10,000 qubits without requiring to have interconnects. These machines are efficient. That means there are tools available, such as qubit shuttling, which can lead to efficient problem encoding and easier error correction. Finally, these machines operate at room temperature. That means it doesn't require any cryogenic facilities, and these machines can be easily accessible by the experimentalist. And again, it reduces the footprint of the machine. The first quantum computer which we built and commercialized is called Aquila. Aquila is accessible through AWS Bracket and also directly through the QuEra's quantum QuEra's premium access package. It's the first and still the world's only publicly accessible quantum computer based on neutral atoms. Recently, we have completed a major milestone in Aquila, which uh, completed 2 years being online. And over the past 2 years, we have increased the availability of Aquila from 10 to 100 hours per week. So Aquila can be used for many variety of application ranging from simulation, optimization, and machine learning. So the next generation of computer we built is a complementary to the Aquila and based on what is called this logical qubit or the gate-based approach. The main issue of any quantum computing platform currently is the noise, appearance of noise. And when this happens, there's a error in the physical qubits. And perhaps that's the most challenging part to solve to make these quantum computers useful for any practical application. If there's an issue, there's also some solution. So one of the ways to solve this problem is to use logical or to use the quantum error correction. And uh, the center of this quantum error correction is the logical qubits, so which are the ensemble of physical qubits. That means set of the physical qubits, which can improve the error rate to the logical operations to a useful levels. So this can reduce the error rate, allows for longer and more meaningful quantum algorithms. The next generation of computer we built is called Gemini. This is based on digital order gate-based approach, and today's we have hundreds of qubits and can be scalable to thousands of qubits soon. And it's an ideal complement to classical super computing centers or to GPUs. It's easy to install machine with doesn't require any cryogenic cooling. It's fairly energy efficient and consumes less than 10 kilowatts of power. It's a very interesting machine in terms because it allows the early access to explore the application of the logical gate-based machines in a co-development modality together with our quantum scientist. So before I finish my part, I would like to focus one of the important aspects of the quantum computer, which is the scalability. If you have seen over the years, especially in last few years, neutral atoms have shown impressive scaling and multiplexing, which is a great news. And there's an image I show you on the right. This is from the lab in Caltech, where they show more than 6,000 atoms are trapped. But to make this trapped atom to a useful quantum computing, we also need some optical controls. And unfortunately, the optical controls has not been scaled in the same way. And and it, given the scenario, we might need hundreds of optical controls. So the scalable optical controls is also very necessary to achieve the uh, uh, quantum computing using this neutral atom. So here at QuEra, we actively following and believe that photonic integrated circuits, which means that photonics devices and some of these optical controls sits on a 1 by 1 centimeter square chip, can solve this issue. And in recent times, we have made very good progress in this photonic integration circuit and covering the wavelength from UV to near infrared. That means covering all the important transitions of the atoms. Our devices are very high contrast. That means the on-off time is very large and they have very high speed and very good power handling. And all of these photonics devices are CMOS compatible. That means they can be manufactured in a commercial CMOS foundries, which is a great news. And we can fabricate very large number of photonics devices. So yeah, with that, I would like to invite Dr. Satyam. Dr. Satyam, if you can please share your slides.
Thanks. It's great to see the progress of quantum computing technologies and various modalities over the last, I would say, decade. And I think there's a lot of interest into seeing how it can be actually applied to industries. So, uh, I'll keep the talk very short. Keep it to some very interesting points, and then we can have a more on the Q&A session. What I believe that quantum is set to disrupt industries, and I'll talk more from the energy industry because I think energy industry is the foundation of pretty much any industry. So without energy, nothing can be done. So before I go, I need to pay tribute to my father. He just recently left the Earth planet, and I'm here because of him. And of course, my family and friends, and I've a lot of work in the quantum world. And thanks to my mentors, one of them who recently got the Nobel Prize, happens to be my scientific grandfather as well. So who brought me into the field of AI directly or indirectly. I'm going to skip this slide. So we'll talk about some challenges, how we think quantum can come to the rescue. So if you look at it, Anshuman just mentioned that the new quantum computer will use 10 kilowatts of energy. Uh, Good to see that, as computing power increases. But look at the total energy spectrum that currently we are using. If we just look at the amount of energy we use today, it's like 8,000 million ton equivalent of energy. And in order to replace, since the world keeps talking about energy transition and energy net zero and these kind of terms, if you just want to replace oil and gas energy, you need all these things: hundreds of nuclear power plants, billions of solar panels, uh, thousands of geothermal or wind farms. Now, just think of it. How do we all these have optimization problem today? Most of the current energy sources have 35% loss in transmission, and that number can be true for many of these different forms of energy. So if you think of it, how much energy is being wasted, this becomes a critical optimization problem for almost all energy sectors, right? And if you look at the cost of efficiency, right, uh, this is, as I said, like most of them are inefficient. So we need to really do simulation on these systems. We really need to optimize these systems, and irrespective of the modality of the energy. Now, hence, quantum computers will actually play a significant role in this sector. Now, just to give you numbers, if since we will talk about investment in quantum, like look at the amount of total energy loss per year. If this money can be saved, we can accelerate the development of quantum computers. You see, it's a chicken and egg problem, if you want to call it. If this can be saved, we can invest in new technologies like quantum, and that quantum air can actually help us recover the cost that is being done. So I just wrote this article recently on how quantum can be helpful in oil and gas sector, and I talk about various problems. But what I really want to focus is there are a lot of news about investment in quantum. Now, some people will say it's going down. Some people will say AI took the fair share of quantum investments. But if you look at just 2024, I think there's an uptick of investment in the quantum space compared to 2023. Of course, number of investments may have reduced a little bit, but overall tickets have increased. So I think it's a good sign. And certainly, I think I was just reading some reports for neutral atom technologies in Europe. There's a lot of push around it. Of course, QuEra is doing work in the UK with the UK quantum mission. But in general, there is a big what should I call push towards neutral atom as well. And if you can look right, the important part is uh, the number of modalities as they are increasing. This will actually certainly filter out some of the areas where the investment will grow significantly. And one of the things that I think recently happened in Germany, if you saw, people started using a new term called quantum data center, right? And now that itself is, if you think of it, nothing special, but at the same time, very special, because the requirement needed to build those data centers is different from HPC. But as more quantum computers are coming and they are being combined with HPC, uh, the layout of these data centers becomes very interesting proposition for actually solving some interesting problems. Now, if you look at some of the areas of who have been really making news in the last 1 year, this list is as you put it out there. This list is not exhaustive, but you can see that the activities in the last 3 quarters has been significant. And from India's perspective, right, since this talk is about World Tour and India, one can see that 2 days ago, I think the National Quantum Mission announced that they are going to fund some 4 different centers, as well as few startups in the area. So this actually shows that there is a traction, and there is speed in which this can be actually integrated into mainstream problem solving, especially when it comes to major areas of energy. So I just want to give you a picture of what's happening, because people have some doubts as to whether quantum. People will ask me, "Oh, when can we see the real quantum problems or problems solved with real quantum machines?" But I think, as we all know, technology evolves and matures. But I think where we are at this point, I think in oh, next, I think two two to less than 2 years or 2 to 3 years, we should see some really commercially viable results, which will actually accelerate eventually the investment in this space. That means what commercially viable means that X amount of investment results in X amount of return on investment, which is significant for a business. And that I think we are in the right time for that. So, since Anshuman also put a term quantum and classical in a different form, I say, is it quantum plus classical or is quantum versus classical? That debate remains. But I think when it comes to especially energy sector, I think it will be always quantum plus classical, because it can't be this or that, because lot of calculations that go into deploying the energy systems can be solved with classical, but quantum can actually help really optimize that, reduce that cost of inefficiency that I was talking earlier. And then, of course, there's a lot of areas where fundamental quantum calculations or quantum theories are needed. One is in terms of, if you just look at the two areas that I just point here, is reservoir characterization in oil and gas. They miss out on typically what is called a long range interaction, which is very important if we really want to know how much oil is left in the world for how many years. If you know the history, oil and gas industry has been saying for last 50 years that oil is there only for 50 years. So we've already crossed that barrier. Every year that 50 year keep shifting. And one of the reasons is that because there is high uncertainty in terms of characterizing how much oil we have. The second is now the very important is the carbon storage. Now that optimization problem is significant around the world, because it is also, if you want to say, it's an opposite of figuring out how much reservoir it is. We are actually using the same fundamental, saying this is the reservoir. If I'm this much reservoir, this much oil we have taken out, then this much carbon we could put in. But there is much more physics and geology behind the scenes. The other one is like, if many of these challenges, whether it comes to wind or solar or oil and gas, understanding the fluid dynamical property becomes very important. And hence, we really building the quantum theories behind that, which can be really solved with quantum computers, is an open area as far as I see it. So what can we do? We can combine various things in this for the energy 5.0 paradigm. That means we have to use quantum simulations, quantum computing for optimization, HPC, quantum machine learning. All these things have to really come together to really solve and build an automated system, which eventually would lead to what I call a quantum platform. And that is the future, I think, and this will help all of us as we move forward. Right. So understanding energy depends on our understanding of arts and science of the basic particles, and basic particles can now form these computers, which is really promising to see that we can actually leverage that. So it's time for many industries to get disrupted, and I think quantum computing, along with machine learning, has multiple uses in like energy, right? And disruption is essential. If we don't know how to disrupt, then somebody else is going to disrupt us. So with that, then this disruption is about talent actually. How do we bring the talent for this new field that is growing faster than anything? That's all I have to share.
Thank you, Dr. Satyam. Great presentation. So, Amit, you are next, so you can try to upload your slides. And while Amit does that, Dr. Satyam, let me ask you a quick question. So, you've been living in US for a long time. You have seen both India and the US and studied in India here as well. So, what lessons from your experience in the US can India adopt to build a thriving quantum computing ecosystem, and how we can leverage the local talent and develop training programs that meet global standards?
Thanks, Anshuman. Interesting, right? There are a couple of things to watch, right? I think even today, if you look at it, the highest number of students who are studying or self-studying quantum computing or quantum mechanics or quantum related courses is one of the largest in the world in India. Whether it is through the companies that we all know on their platform or open source platforms that exist. Uh, Whereas, and hence, if you look at in general the number of people employed by various quantum companies, you can see a lot of people who have been trained either in India or of Indian origin trained outside in this field. But where acceleration is needed is in terms of India taking advantage of it is actually collaboration in terms at the academic level, at the industry level, as well as the what do you call the governmental level, right? If you look at it, there is lack of mentorship for these people. The industry, unlike if you look at Canada, large amount of investment has come from private companies into this area and helping accelerate the development of hardware and also the toolkits. Whereas if we look in India, I don't see much of private investment really. Yes, there are companies which are in the service industry. They are doing because they can build global partnerships. But in terms of major industrial groups, that that doesn't exist. So lack of knowing what problems to solve for India is a big gap, I think, in terms of how we can accelerate quantum uh, development in India. Like I used to work, I used to go to China quite a bit many years ago. I stopped going there now. But you can see that one of the things that they implemented very early on, partnership with private companies as well. So I think that private large industrial groups need to really step up in this process and actually collaborate. I think quantum, we all know, those who are working in this space, it's a collaborative effort rather than saying I can build my silo, you can build my silo. That's not going to work very well.
Thank you, Dr. Satyam. Amit, floor is yours.
Yeah, thank you. Thank you, Dr. John. So I would like to start with this background that is set up by Dr. Satyam. So when we talk about CDAC, CDAC, as you all know, it's a supercomputing organization and in India, and we are known for our Param supercomputer. And thanks to Dr. Vijay Bhatkar, who was the founder of CDAC, and these are our initial Param system, Param 8000 and Param 10,000. So that were like the first supercomputers in India. After that, we have got our national supercomputing mission, and government of India has given us a mandate to establish various supercomputers across various IITs and various NITs. So in this series, we have set up various supercomputers across the country, and our supercomputing power of the country has been grown enormously by using this national supercomputing mission systems. You can see various systems installed, and this is an ongoing thing. So we are having this Param Siddhi and Param Eravat at CDAC itself. So this is like a higher AI HPC system. Now when we see HPC is like integrated with the AI, so we are seeing artificial intelligence and HPC linking together. We can see it in Param Eravat. Now next comes the era of the quantum. Now we will be definitely seeing HPC, quantum, and AI playing a important role integrated together to solve the grand challenging problems. So with this, CDAC is having a mission in the quantum technology to align with the national quantum computing mission. So, so based on that, all our works that we are doing, we are aligned to NQM, National Quantum Mission, and then we want to create an ecosystem that will help all the quantum computing experts, researchers, students to access various access platform where means they can develop a lot of new algorithms. They can develop a lot of new problem solving environment where they can solve the grand challenging problems. So this is what we can provide as a platform. Now when we say national quantum mission, so under the national quantum mission uh, there is a stress on like how to take our country forward in a lot of quantum technologies. So we can see that India has started and we have already developed like 6-qubit indigenous superconducting based quantum computer that you will see. And now this is start, and based on that, now since National Quantum Mission is there, so we are like scaling up the systems and we are making a full ecosystem where we can make a vibrant environment mostly, and we want to cover the startups also. We want to grow a lot of startups which can work in this quantum technology area. So a lot of focus on developing the quantum potential, as well as this developing a lot of startup ecosystem across this. So National Quantum Mission has actually divided this quantum technology. It is for quantum technology. So they've made 4 hubs. One is quantum computing, communication, sensing, metrology, and quantum materials and devices. So based on this National Quantum Mission is aligned, and it's not like that we divide it into 4 hubs. These all the 4 hubs are also interacting with each other. So they work in synchronization with each other so that the problem can be solved together. So when we see the quantum computing expertise in India, there are a lot of academic institutes, there are a lot of IITs which are working in this, already working in this area since last maybe 10 years and more than that. And we have various programs in our country, like Quest was there, which was the initial of before the National Quantum Mission. So a lot of foundation has been there, and our Ministry of Electronics IT has already played an important role to set up a lot of projects in this quantum computing area. So we can see the superconducting based things, photonics based things, and trap ions based things, and other technologies. A lot of institutes are there in India working in this technology. Then we see dilution refrigerator also. VCC Kolkata is there. They are working on the development of this. Then control and measurement electronics, CDAC itself is doing. There are startups like QPI. They are working this. A lot of ISCs, IITs. And then when we talk about the software HPC quantum integration, you can see IIT Roorkee is there, CDAC is there. A lot of you can see startups as well as academic organization as well as government institute, research labs, all are working together on these focus areas. Now, when we talk about the framework, so we have developed a QSIM framework in collaboration with ISC and IIT Roorkee. That QSIM is available freely to all. You student can access. This is like if you just type qctoolkit.in, you can access it. It is open, and it is like a workbench where we can have a composer. You can compose your circuits and you can execute this on a simulator at the back end. At the back end, we are using our supercomputers for this execution. Then there is Center of Excellence in the Quantum Technology, where we at ISC we have developed this 4-qubit quantum computer, and we have developed our own indigenous control electronics that controls the 4, and we are scaling this control electronics. Then recently, DRDO with TCS and this TFR, I think Dr. Shridhar will be talking about this. So this they have launched 6-qubit quantum computer, which I think TCS will be taking it forward by providing access to the cloud. That is going to be a great achievement where this quantum computing facility will be made available. So in our group, what we are doing, since we are HPC organization, we are working with accelerators. Right now, what we are doing, we are having the simulators. Now, these simulators we want to accelerate by using GPU, vector, and FPGA based accelerators. So that project we are working. Now, our major mandate is to like HPC quantum integration, where we are working on the various application areas, and these applications already we are solving by using our HPC systems. Now, how these HPC applications can be integrated with our quantum computing workloads, and how we can make a hybrid quantum classical use case, solve these grand challenging problems. You can see all this framework like Slurm, the OpenACC, all these are the HPC things. And then we have QSKIT, Circ, and all the simulators. And then we have to make a connection between these two so that the hybrid workload can be executed. So based on that, what we have done, we have formulated that we can use quantum computer as an accelerator. So at the left hand side, you can see the HPC based things, which is connected by InfiniBand, those InfiniBand network, and by using a job scheduler Slurm. So when we talk about this compute nodes, they are connected by PCI Express through GPU, FPGA. These are the like accelerator cards in the classical world. And then we have a interconnect network to connect to the quantum computer control electronics. So this is actually what we are working in it in a way so that this quantum computer and the HPC can be connected through some physical layer, and then these jobs can be offloaded. As you can see in the right hand side, the CPU workload and the quantum workload can be separated So there can be smart compilers which can there can transpilers, and then there can be offload mechanism of that. So these offload mechanism can offload the quantum task to the quantum computer, and whereas the classical task can be executed by the classical computers. So one of the example is like VQ hybrid execution flow, where this classical and quantum, they just interact with each other and execute this workload. So we are looking forward to develop an open quantum ecosystem where from the application to the quantum pane, everything is going to be an open system where everyone can collaborate, everyone can contribute in whatever layer they want to contribute. So this is the like a plan that we are having. We are going to make an open quantum ecosystem where at every level everyone can contribute, and through the international collaboration, through the national collaboration, through the academics, through the researchers, through the students, so this total system ecosystem can be developed. Particularly we are working toward, you can see at left hand side we have a concept that param q, so that quantum computer, and then we are going to integrate it with our supercomputer, where you can see right inside this params with the AI. This system is already there. Now, there are a lot of challenges to connect those two systems, and connection at a logical level, at a physical level, at a programming level, at an level where this both the job scheduler, they can understand about the quantum computers as an accelerator. So all this total software framework has to develop. So we are working in that direction. Now, CDAC focuses, as we are under Ministry of Electronics and ITI, so we focus mostly on electronics and the control system software, and we want to develop with the industry, academia, and based on that, our problem statement use cases can be solved by using end user agencies help, and then we can evolve technical milestone and market milestones. So based on that strategy, we are working. Now, what I want to highlight is that in India, as per this McKinsey report, India is the country with the highest quantum talent. You can see the Europe, but Europe is not a country; it's like a union. So when we see India as a country, we have got the highest talent, and lot of students, they have a lot of enthusiasm to work in the quantum technology. I can see. So if we develop in India a proper training module where the students can start using this quantum computer, they can start developing. Definitely, India can be again like we have the IT superpower. So similarly, in the quantum software field, India can again be a superpower, and then we can develop a lot of softwares in this quantum technology, and mostly in the HPC quantum hybrid scenario. So this is what actually CDAC is pushing, and our ministry is pushing, and National Quantum Mission is pushing to move in that direction. And we can solve the grand challenging problem not only for India, but we can solve the grand challenging problem for the world and for the humanity itself. Like you can see drug discovery, those are the applications. Like recently we have this COVID era where still there is no medicine for the COVID. Why there is no medicine for the COVID? Because it's a lot of simulation is being required, because there are millions of drug targets, and with the COVID molecule, how. So this is one of the example I am giving. Then there are various optimization problems where like airlines and then transportation industry is working. So all these grand challenging problems, if we try to solve by using quantum and HPC together, and one of the most important factor in the quantum technology is that the energy efficiency, which Dr. Satyam was talking. So HPC, when we are moving toward exaflop, huge power requirement is there. And in this scenario where we are moving towards a green energy and those type of aspects and sustainability, definitely the role of quantum becomes very important as an accelerator. So HPC quantum integrated system with the low power consumption, we can definitely solve a grand challenging problem by using this combination. Thank you.
Uh, Thank you, Amit. Thanks for making very nice presentation. Shridhar, you are up next. And while Shridhar is uploading his slides, Amit, let me ask you a quick question. So when you consider HPC integration with quantum computers, what are the important factors, when selecting a platform, like, for example, superconducting, trap bands, or neutral atoms?
Yeah, when we typically see HPC supercomputers, it's like a big, we can say, data center, and then there is a lot of noise, and there is a lot of cooling requirement, and then we have chillers, and then a lot of vibrations are there. Now to have a quantum computer just near to this type of environment, a lot of things has to be taken care. Like first of all thing is that it should be like capable of handling those type of vibrations, noises. Second thing is that the cooling. So the most optimal thing is that the like quantum computer that works on a room temperature base. Then we are having coherence time, fidelity. All these aspects play a very important role when choosing a HPC quantum integrated system, because keeping a quantum computer in the vicinity of this HPC is a very difficult task, specifically when we have a lot of vibration, lot of noises, not a lot of environmental effects. So all these aspects in the quantum computer has to be taken care while choosing a system for the HPC quantum integration.
Thank you, Amit. Thank you very much. Shridhar, floor is yours.
Yeah, thank you, Amit, and thanks, Anshuman. Yeah, yeah, this is Shridhar from the TCS Quantum Initiatives team. Yeah, this is a quick introduction about TCS. So we are India's largest IT company with about $30 billion of revenue and with over 600,000 people. We invest about 1% of this in the corporate research and innovation, so which is about $330 million. Quantum Initiative is part of TCS research program. So we have a excellent research team which focuses on different sciences. So one of the areas that we look at is the future of computing, so under which the quantum research group falls. And the innovation is based on collaborative approach. So we have something called COIN, which is the Co-Innovation Network, where we collaborate with academia, startups, accelerators, venture capitalists, and alliance partners, and so on. And partnering with this ecosystem, we try to build these high-risky emerging technologies and place bets on them. It's also important that we showcase these technologies as we build them. So we have created something called PACE network, so where we have showcase centers. So these are our innovation showcase centers across different countries. So we have the innovation center in New York, London, Amsterdam, and multiple places, 10 different centers globally, where we demonstrate whatever research that TCS is building is demonstrated here. The some numbers are here. So a large research team focusing on building, placing bets on almost every emerging technology that is out there. So just deep dive into quantum a bit. So quantum started as a research program long back, and then in 2020 we saw the trends are shaping up well, and then we thought maybe it requires a different team, and we created an incubation program for quantum. So initially we started focusing only on the software, but only on building algorithms, etc. But later we realized, okay, we need to expand this a bit into very specific focused vertical specific problems, and then started working on problems in AI, ML optimization and simulation on the computing side. And then we started another team for security. And then this is also another emerging area that we found very interesting on sensing area. So we have teams today. We have teams working on all these three areas. So computing side, so we have AI, ML optimization and simulations, security and sensing. So the advantage for TCS is we are already working on a lot of optimization problems for many customers. And then there are also many AI/ML projects that are going on. They are also in the early stages, but there is an opportunity for us to take the same projects and reimagine them with quantum. Because so there's a lot of hype around solving problems with quantum. So we started journey there. And when we started, it was around 7 qubit that was available from IBM. And then we can do better work on simulators with 22 qubits. And that's how we started the journey. And numbers look a little different today. So like Dr. Satyam mentioned, so it's more of an ecosystem play. So we work with different ecosystem partners here in terms of learning as well as building the technology and as well as solving some grand challenges. So in last year we floated a hackathon, global hackathon, where we floated some 4 problem statements, and it was nice to see a lot of interest from different players globally in solving those problems and submitting their solutions for these problem statements in quantum. So that's extremely interesting. Another advantage that we have exploited is basically we have a huge customer base across different verticals. So there are always early adopters who want to be innovative. So these are customers who are willing to work with us. So we have got an opportunity to create few projects. I'll cover them in coming slides. We created few projects and then explored jointly along with them in terms of scoping the problem and then solving those problems and see what are the proof points that quantum can give now. We evangelized this technology to more than 100 customers of TCS and collaborating with many adopters. So there's a lot of interest, a lot of curiosity from the customer side today, and they don't want to miss this bus. Amit mentioned about the HPC integration with quantum. So so we also are trying to see, so how will the infrastructure in 2028 will look like, say. So when we try to map these two technologies, so both the classical as well as quantum, so there's some good emerging trends that are happening. Right. On the classical side, so we are seeing this, the nanometer scale is reaching about 3 nanometer chipsets that are available now, while 7 is very common. There are a lot of new entrants who are actually building these chipsets on 7 nanometer scale, which are as good as the legacy leaders like Intel, AMD, and Qualcomm. So a lot of interesting things are happening on the Qualcomm side. Also, new startups have, on the classical side, and also new startups have entered in the space. So which is actually shaping up very well on the classical side. So today I can simulate, say, on a basic laptop, I can simulate about 22 qubits. If I go to a HPC systems, I can go up to 45. And we've also seen research around 50 plus qubits simulating on HPC systems. But with classical architectures getting better, so probably we might see even better architectures here as well. So now coming to the quantum side, so again, there's a lot of progress here. So we're talking to multiple vendors who are making the quantum machines. So we see the proof points or the pointers that are coming in terms of these machines are data center ready. So they're are also becoming network ready soon. And then there's a talk of quantum memory. So these are three different trends that can actually transform and create a ChatGPT movement for quantum computing. So while we may talk about small number of qubits today, but suddenly if we have these capabilities of uh, networking them and having good memory, quantum memory, so we can go to a higher scale and suddenly the landscape will look different. So it's important. So we also believe that both coexist, the classical and quantum, and then, but how the future infrastructure setup will look like is something intriguing always. We had a lot of learnings so far. I think skills are one of the major gaps. So what we have done is, right from the beginning, we've kept our focus more on the software side, while we depended on the hardware coming from the pure hardware players, except for we made one bet with the 6 qubit quantum machine with superconducting technology. But rest of the times, so our focus was mostly on creating these novel algorithms and customizing these novel algorithms for very specific solutions and solving these vertical problems. So this is the play at which this is the play we are operating in, and I think we believe so. A lot of things are happening on the hardware side, which will, and we will also have to work together with them in terms of reaching this quantum advantage for solving the problems. Coming to some of the use cases that we're working on, so these are some of the use cases that we tried with our customers. So these are all collaborative efforts. So you can't say that there is a clear commercial advantage today. So right from the BMW Quantum Challenge, we've been participating in everything that is coming as a challenge in quantum. So these are some of the problems that we're working in AI. So basically, image processing methods. Still, the value. I mean, you can establish that there is value, but it is very expensive to utilize a quantum computer and generate uh, that kind of utility. So that makes it very difficult to define the scenarios for ROI. We've also tried problems related to forecasting, optimization, etc. So in case of drug discovery, you've seen some success. We're working with some of the leading players in the pharma industry. So here we're using a kind of hybrid approach, classical quantum approach, and then showed some utility here. So even the customers are excited. So these are early days. So we published some nice research here. And from the security point of view, there's I think there is ever since the NIST has announced the new standards because of the quantum threats that are emerging from quantum computers. So we again see a lot of customer interest coming in this area, which is again beyond quantum. Some more examples of the use cases that we had worked on. So these are efforts with our business groups, and some with our customers, and some with our partners, and some are floated as challenges. I think we have enough examples. So all these done at small scale, which are enough to say that, okay, once we have a big size quantum computer available, so we are ready to take up bigger challenges and solve these problems. But again, it's important to watch how the quantum computers will evolve over the next few years, and then see how we can actually uh, be, really harness the power beyond the classical computing. In terms of collaboration, so this is extremely important to work with the ecosystem. These are very risky technologies. So right now we partner with multiple academic institutes in India and abroad, and try to work on certain very specific areas. So, working on quantum computing with TIFR, where we build the software layer and then try to solve these small size problems. On sensing, we made some very nice, interesting partnerships. So some of them are also part of the National Quantum Mission. So here, again, we help them with the firmware and the upper layers of software development. So we're also part of the broader ecosystem, the Quad Task Force and the National Quantum Mission, and also working with the India's education regulator for building the workforce for the country. So we're part of framing the syllabus on how the quantum graduate degree should look like, and then making sure that all the key concepts are there so that we get nice workforce going forward. So this is an example. This is the quantum challenge that we had floated last year. So we've taken few customers' problem statements and partnered with AWS and the UKRI, and then we floated this as a challenge. We got nice responses and very innovative solutions through this one. So most of these are open sourced, and some of them will be up, can be seen on GitHub. I think the quantum security is another buzz area, so which is where we are seeing a lot of activity right now. I'll not spend much time on this one right now. So the way we are approaching right now, so we see a lot of customer interest. So right now, we call this framework or quantum value discovery approach because coming from industry, so our customers are looking for immediate value right now. What is there, right? So, but it's extremely difficult. We all know that the inflection point may be sometime 2-3 years or maybe 5 years away. So we try to establish these 16-week pilots with these customers, and then go in an iterative mode, and then ensure that the entire organization is also trained on quantum, explained with the benefits of quantum, and then take some of the use cases that our customers have, and then try to solve this on a small scale within a very short duration, sometimes at no cost or less cost. Right. So, and this is what we are trying right now. So as we get better and better quantum machines, customers are also trying those problems again and again. And so we have this last phase, iterate and scale. So I think till we see the inflection point, I think this is the model in which we operate and establish the initial proof points of value and then move forward. Just on the quantum initiatives in India, so Amit covered about the National Quantum Mission. So TCS is very well part of this mission, and also collaborating with a few technology groups which are in sensing and computing. So closely working with them. So I think government is doing a great job in rolling out this mission. So as of September 30th, they've launched 4 hubs, and these hubs are getting operational now. And then so last month, November 26th, the government has also given funds to 8 startups which are working under this mission, and they're contributing to so interesting complementary technology areas which will help the mission. So between startups, academia, and industry, few players like TCS, Tech Mahindra, HCL, L&T. So we are all working in quantum in India. So between all of us, so we are collaborating. So we have a very rich ecosystem now. And there are more than 100 plus startups in the country as of now, plenty of academic institutes have been working on quantum for some time now. So I think the ecosystem is shaping up very well. So going forward, we'll be able to tap and exploit all the opportunities that are coming out of this space, and then I think so we'll build great value for the mankind. With that, I'll conclude this session. Thank you, and back to you, Anshuman.
Yeah. Thank you, Shridhar. Thank you very much. So yeah, so let me start sharing with my slide. And Tommaso is all stage is yours, but before Tommaso gets ready, Shridhar, let me ask you a quick question. So I think Amit has touched on that India's very strong foundation in software development and a significant advantage in the global quantum landscape. How do you see TCS leveraging this strength to develop quantum algorithms, software platforms, and tools?
Right. I think there are two perspectives, Anshuman. So one, we already are solving many AI and optimization problems, and there's an opportunity for us to reimagine all those problems with quantum and see how best we can solve. And then second, coming to the talent part of solving these problems, because we know people who can solve this classically. So we also train some of them to shift their mindset to solve the problem in a quantum way. So which is little difficult. So luckily, our team is organized in such a way that we have people who can transform a problem from classical domain to quantum domain and run it on this one. So which is something good. And second, we also, because there's a rich ecosystem outside, so we also got very nice interns from the university who worked with us in solving some of these problem statements. So that is really helping us.
Yeah, thank you. Thank you. Tommaso, it's all yours now.
Thank you, Anshuman, for of course, for the possibility of being here, and of course, I would like to welcome all our guests from today. Anshuman, please go to the next slide. So my what I would like to highlight during this last part of the presentation are sort of commercial engagements of QuEra. Recently, we announced a significant investment, strategic investment in QuEra from Google, that of course you all know. And as Anshuman mentioned at the very beginning, we also opened offices both in the UK and in Japan, thanks to the signature of important contracts to install QuEra's machines in the UK through the so-called UKRI initiative, the UK Research and Innovation branch of the UK government, and at IST, which is the equivalent of the National Institute of Standards located in Tokyo, in Japan. And this will be an initiative done together in collaboration with NVIDIA that will basically create a local big supercomputing center, classical supercomputing center powered by their GPUs. So, Anshuman, please, the next one. There are several ways to, of course, to collaborate with QuEra, and hopefully over the past few slides, presentation from Amit, Dr. Satyam, and Shridhar, you got a sense of the opportunities that we could basically realize all together within the Indian ecosystem. I would like to highlight three of them. First of all, the possibility, of course, of acquiring one of QuEra's quantum computer and collaborating, of course, on the development of use cases, but also having direct access to QuEra scientists and engineers for the installation as well as support and the development of the local community. The second one, which is sort of which lowers the barrier to access to quantum, is a standard cloud access. QuEra is already partnering with AWS to provide access to our third generation machine called Aquila through the AWS Bracket service. And we also created recently a so-called premium access model where researchers or any end users can also connect directly with QuEra scientists to have mentorship and support in the development of academic or industrial use cases. The third modality is what we call the co-development model, where we would like to establish long-term strategic collaborations with partners to go develop what are called the killer applications of quantum computing across several business verticals, or even more particularly with what concern academic applications. In this spirit, we developed what is called the QuEra Quantum Alliance, that by now counts more than 20 members across the globe. And the goal here is to essentially facilitate the access to neutral atom quantum computing through a direct partnership with QuEra. With the alliance, we plan to organize several activities, so both in-person meetings as well as strategic collaborations, again, to develop applications and to provide access to our technology to the local communities where these companies and organizations are based. So with this, I think that I hope that we sort of created all the groundwork in order to stimulate potential collaborations with us, and not only with us, but also with the partners that you heard from in today's presentation. If you're interested in joining partnering with QuEra, feel free to reach out to us. This is my email, tmacri@quera.com. With this, I would like to pass the word back to Dr. Anshuman for some final remarks, and thank you all for the attention.
Thank you, Tommaso. And yeah, that's pretty much all we have for this webinar. And thanks for joining. And yeah, and until next time. Yeah. Bye-bye.
Thank you.
Bye now.
Thank you.